doubt about that. So now I'm move on to the lecture. So now can you see the screen? So now,
Yes, sir.
okay, so there was some glitch, so that was not functioning, but okay, now if everything is clear, we'll just move ahead. So today we are going to start a new topic that is on trust. Actually, so far, what we have studied was theory behind equilibrium of force systems. So you have studied what are the equations to be satisfied for a planar, for a rigid body in a planar system, for coplanar system. So those were basically forces, Fx, Fy, and moment. They all have to be, they have to be balanced. Okay. So that was the conditions of equilibrium, two forces, two force component, two force equations, that is Fx omega and moment equation that have to be zero. So they have to be balanced. Now, in this trust, what we do is, what we'll look at is the application of what you have studied. Those are theoretical concepts, and this is trust is an application of the theory for to some practical problem. It is not a problem for in practical design. So you know what is a truss? Any idea what is a truss? Have you heard of it? Okay, so not an issue. So we'll first we'll see what is a truss. So this is the truss originates from the word truce. So meaning collection of things bound together. So basically, it is sort of a etymological perception or so the origin of words. So that is the aspect here. So it is interesting to note that the word has the origin in the French, in the French language. So it is a truce means collection of things. So what are truss basically? Truss is basically is a collection of structural elements like you see in this figure. So basically, this sort of arrangement, structural arrangement, you will see in the bridges. So these are like a railway bridge or it is mostly the railway bridge or bridge over across a river. So this sort of arrangement is there made. So basically, this is called a truss system. So why they are employed? They are employed to support transverse load. In this case, if you see, this is the axis, horizontal axis, horizontal direction. The transverse load are vertical loads. So they are the vertical loads. So supposing you want to cross this river, that is a huge, you can see a big cavity here, or it's a large space there. Then basically you have to lay some structural elements here, structures, and you have to cross it. But if you cross it, basically, then your load has to be borne by the structure, otherwise it will collapse. So this sort of a truss structure is so designed so that it can carry the vertical load. Suppose you want to move in a car or a truck, basically that during that movement also, the bridge should remain intact. That is the intent. So for that, you build up a system. Okay. So this is a truss. So truss is basically is a collection of members so as to what is the function to support transverse load. But if you see this member, which is a typical member, here the loads are always axial. as you have studied that for a member to be in equilibrium, the load has to be axial, and they have to balance each other. So this has to be, this is collinear. So for this case, for this member to be in equilibrium, the forces have to be axial. So without that, if there is non-axial forces, if their forces are not axial, then they will have a moment and will have rotation. But that is not happening here. So forces are axial. So one thing you have to notice, the entire truss as a body, as a system, it is withstanding axial. It is withstanding axial, this transverse load. So it is withstanding transverse load, but the members are internal forces. It is facing. It is basically subjected to axial or axial load. So although the members having axial load, overall the truss system is supporting transverse load, but the members are subjected to only axial load. So that is one thing you can just keep in mind. Okay. So your this bridge or this truss is supporting these vertical loads here, but in the member the load is not vertical; it is always axial. So this is one thing to note. And this is general typical figure where the truss systems are applied for the bridge. So this is called the bridge truss, as the name implies. So this is a bridge, and this is a truss system to support the moving load on the bridge. So this is a car; it is moving on the bridge, and this is the deck. This is a deck on which, or you can see the tar or the black top of the road, and you see this. Structural arrangement is all done just to support this vertical of the car. Okay, so this structure has to be carefully designed so that this what are the applied loads are adequately resisted. So that is the intent. Next, we move on. So this is a figure showing a plane truss. Why it is a plane? Because all the members are in a plane. So AB, AC, BC are members and they are in a plane. So it is called a plane truss. A framework composed of members joined at their ends to form a rigid structure is called a truss. So that is the definition of truss. A framework composed of members joined at their ends to form a rigid structure. So they are joined at then, so A and B, this member is joined with B and C at B, which is the end of A and end of member AB and end of member BC. So they are basically connected at the ends. So bridges, roof supports, derricks, and other structures are common examples of trusses. Structural members are commonly used as I-beams, channels, angles, bars, and special shapes which are fastened together at their ends by welding, riveted connections, or large pin bolts. Large bolts are pin. When the members of the truss lie essentially in a single plane, the truss is called a plane truss. That is shown here. And the structural members are generally I-beams. For your general knowledge, you just remember this term: I-beam, channels, angles, and bars. These are basically used for this structural construction. If you go to some site where there is a lot of structural construction, like your metro rail, etc., you'll see some steel members lying, and they are basically I-beam, channels, angles, etc. So I-beam is, just for information, I-beam is steel section whose cross section is like an eye. Okay, so this is an I-beam. And channels are basically like a C. If you take a cross section, it is like this. Okay. Angles are basically L that you normally use in your domestic construction also, like a shelf, etc. You have that angle where you weld a bracket. And bars are bars, that TMT bars, etc. These are just a cylindrical structural elements. So they are for various purpose, and TMT bars are basically a company. They are for reinforcement in the concrete. Okay, so these are some structural components which are used in construction. Um, you can also find a roof truss, which is a three-dimensional truss. So basically, this is also used where it is basically you are having a three-dimensional, very big structural configuration to support. So there you have to have three-dimensional support for the structures. So there you have three-dimensional, or it is called a space truss. So basically, if you see those stadium, etc., where there are some global dome, etc., on the top, so the supporting is mainly done by this three-dimensional, because the dome is three-dimensional. So these are basically some applications where you have the trusses. Okay. There are different type of trusses, and that we'll see. And if you see, this is a bridge truss, and we have one end which is pin connection. That is pin connection that we had emphasized in the last class. It has only two. It can have reactions Rx and Ry. But it cannot have any moment, because this can be free to rotate. Okay, it can only resist forces. So it will have forces Rx and Ry. So this is Ry, reaction force, and Rx. That is force in the horizontal direction. That means this pin will not allow the truss to move in the X and Y direction, but it cannot prevent rotation because it's a pin. It can just rotate. So there is no moment restraint here. And here it is a roller, as we have discussed last time. It can only apply a normal force like this. Okay, so it can apply normal force because roller can move. So can you tell me from common sense why for this bridge, for this truss, you have a fixed point here, fixed end here, and a rolling end over here? Can you tell? Any guess why?
So for thermal expansion.
Yes, correct. So because of thermal expansion, you need some movement at this end. Otherwise, if you fix this, then basically you cannot. Actually, if you do not allow the thermal expansion, there will be huge stresses, and that will be basically failure at those joints. So it is very common in big bridges. Also, you'll find some gaps. So there, basically, they allow the elements to expand. So here, the same principle. Normally, at this truss, one end you will find fixed, and one end you'll find a roller, just to allow for thermal expansion. So there are various types of trusses. These are they are known as Pratt, Howe, Warren, Kay, and Baltimore. These are shown in this figure. Okay. So this is a Pratt truss. This is a Howe truss. This is a Warren truss. This is a Kay truss and Baltimore truss. This Pratt and Howe are almost same. It is just inverted. You see, this is a V. This is a V, and here it is inverted V. Okay, so this is almost the same thing, the same configuration. This is a Warren is a combination of both Pratt and Howe, as you can see in the figure. And this is a K truss. In fact, you can see the configuration is like a K here. Okay, that's how we got its name, K truss. You just try to just remember this K truss. It will be used in the future discussion. So this is a K truss where the shape is like a K, and these are Baltimore truss, etc. So there are various type of truss. These are basically bridge truss. So for a bridge, so the configuration of the truss is mostly like this. If you just travel in a railway or you watch the bridge from outside, you will see this type of structures normally. And these are the roof truss. Actually, this means if you have the workshop shed, locomotive shed, or you have an outdoor entertainment program, outdoor programs, so where you open air programs, there you have to have that shed and you have to have that canopy, etc. You have to cover. So there in the roof, you have to support it also. Otherwise, you cannot have that full cover of the roof. You cannot leave the roof unsupported. Otherwise, it will collapse. So in the roof, you have different types of trusses. So this is Fink, again Fink, Pratt, Howe, Warren. There are various type of trusses used in the roof. So they are used. So trusses are used in the bridges as well as on the roof. You have to have a very big, you have to build a very big shed. Okay, then you have to have a very big roof, and for that you cannot just have a roof without any support, and they have to support it from the top because you have to keep the space free for human movement. So you have to cannot keep any columns directly up to the ground. So you have to support it from the top. So that's a roof truss. Okay. So now let us now go. That was some description. Now let us go to some theoretical aspects. How to construct a truss? So first, let us see this example where you have 4 elements: AC, CD, DB, and AB. There are 4 structural members, rigid members, connected at the pin joint that are shown in circles. Here, if you just tap any corner C, then you will see that the entire structural system collapses. Collapses means this the angle between the shape will completely change. That means the angle between the 2 members will completely change, which will be much different from the initial configuration. That means they will not be stable. That means with a small force, the configuration will be changed to a great extent, that drastically. So it means that it will collapse because you want the configuration to remain intact even after the forces are applied. So basically, in this case, the 4 in this quadrilateral, the structural member made of 4 members, the structural system made of 4 members, pin jointed members in the form of a polygon. Here it is 4, but it can be 4 or more. It will collapse under the action of external loads. Then how do you make it stable? To make it stable, you have to do only one thing. You have to just join this diagonal. It is braced to make a triangular configuration. So now you have 1, 2, 3 triangles, and a triangular configuration is very, very stable. So it is stable. So basically, from you have to see that if you find there is a problem of the stability, that means the structure is not retaining its shape, then you have to move on. You have to just see how you will make it stable by adding members to make triangular configuration. So adding a diagonal member stabilizes the structure, and this is a common practice of making trusses. This is a common practice of making trusses, but this is not the only way. You can also have rigidity otherwise also. So, but this is a very common way of making the structures stable. So, the takeaway is, if you have a triangular configuration, then it is stable. If you do not have, then if you have a polygonal configuration, it becomes unstable. So that is the main takeaway for this. So simple truss, what is a simple truss? Simple truss is built from basic triangle. So basically you have this triangle as we have seen. So structure built from basic triangle in the manner described are simple trusses. When more members are present than needed to prevent collapse, then the truss is statically indeterminate. A statically indeterminate truss cannot be analyzed by the equations of equilibrium alone. Additional members or supports which are not necessary for maintaining equilibrium configurations are called redundant. This you will understand later. This you will not understand now, but just go through the terms. Redundant, statically indeterminate, and redundant. Redundant literally means more than required. That means that if you require 3 members for the structure to be stable, and if you add more members, then the additional members are redundant. So that is what it says. And simple trusses are basically composed of basic triangles. So that is the definition. So how do you represent the truss for analytical purposes? That is for your calculation or designing. So truss is basically, as we have discussed. Yes. Any doubt? No. Is there any doubt or anything?
यस सर, सिंपल ट्रस एक बार और बता देते।
नहीं समझा, नहीं क्या सिंपल ट्रस्ट?
उसमें कंफ्यूजन है, पूरा क्लियर नहीं हुआ।
हाँ हाँ, कौन सा क्लियर नहीं है बताओ ना, कौन सा क्लियर नहीं? ट्रस्ट, व्हाट इज अ ट्रस्ट, क्लियर है?
यस सर।
हाँ, so simple truss is composed of, simply built from a basic triangle. Okay, here ये देखो, here we have this truss system based on basic triangle. This is one triangle, this is one triangle, this triangle another triangle. Okay,
यस सर।
so this is a simple truss where truss is built out of basic triangles.
अच्छा,
ठीक है?
ठीक
So
है।
so this truss is basically, if you see a truss is a structural member, that means it is having all the dimensions, is having depth, it has having length, etc. But for calculations and design, you need not capture all those parameters in your design. You, for representation, what you represent is only a line. So AF is a truss. In our calculation or analytical expressions, we use only, idealize it only the straight line. Okay, so if this is actually figure of that picture of more or less some representative model of the actual truss in the field, but for analytical purposes we just represent it with a line here. This element AF is now here, it is AF. Okay, so a line and with two nodes, two circle, that represents the joints. So this F is a joint, A is a joint, and then this is how it is represented. Similarly for other elements, so this will be E, and you have to number the nodes, that is joints, A, B, C, D, and so A, B, C, D, E, F. So these are the nodes, and the structural members are basically AF, FE, BF, BE, CE, and CD. Okay, and the loads are basically applied at the joints, so they are not applied in between. So the loads are basically applied at the joints. So you have external loads at these joints, and these loads have to be resisted by the members. So that is the whole exercise. If you apply some load at the joints, then the question is, what are the loads generated on the member due to the application of loads on the joints? So, and this you have to calculate, and this is what the exercise which you are going to do. You will be given a truss configuration, you will be given some applied loads, and from the applied loads you have to calculate the reactions and also the internal loads which are developed in the members. So basically this is the whole summary, or you can say bottom line of what the activities you are going to do for a truss. Now something you have to understand. If you don't understand, you can stop me and I will try to explain you more. See, this is a two force member because there are only two forces acting, that is one end and the other end. There are no other forces acting in a truss. So where you have this forces which are collinear, there can be two types of forces. One is tension, which is stretching the truss, and one is compression, which is compressing the truss. So this is how it is represented. This is at the ends, but at any point inside you can just cut a section, and at this end, the lower end, you will find the force upwards, and in this and for the upper section you will find the force downwards, and for this tension, and reverse for the truss, which is in compression. So if you just imagine a cut here, in this cut the force at the bottom end is upwards, so basically this has to be balanced. We have a compressive load over here. So this is compression. So in a truss, basically you have three elements. One is the joint, and one are the two members which are connected at this joint. So basically in this joint, if there is a compression, then we designate the compressive load in this manner. The force towards the joint is compression, and the force away from the joint is tension. So that you have to understand and you have to be very clear in your conception. When there is a compression, we just we represent it with the force towards the joint like this, and when there is a tension on the member, we represent it with the force away from the joint. Okay, this is tension, this is compression. So you just pause here for a few seconds, then try to understand it and then move ahead. If you have any doubt, then you just tell me, because later on you'll get completely confused which one is tension, which one is compression when the truss becomes a bit complicated. So you have to have your conception absolutely clear at this stage. So here the forces, I am again repeating, forces on this member towards the joint is compression, and forces in the member which is developed due to the external loads away from the joint is tension. So these two things you have to keep in mind. Next, in the drawing you can see you are representing the truss very in a simple manner, like you have this joint and you have to this line represents the truss, etc. But in the field, how is it? Is it so simple? Obviously, it is not so simple. It is a bit complicated. So in the field, actually, you have something called the gusset plate. Here, the members are connected to the gusset plate, and gusset plate is welded so that it holds all the members. So in the field, we have a gusset plate, but we are not designing this gusset plate or anything like that. That is part of the structural design. But just to have your attention to the fact that what you are having in the idealized condition for calculation in the field, reality, it is quite different. If you see this, then basically you should not get surprised at how the trusses behave. So basically these are actual physical the physical model of the truss, and in the idealized model we are basically using only straight lines and a joint, etc. Okay, so this is how the truss will look like in the field. So next, the joints in the trusses are frictionless pin joints. So here if you see, it's a pin joint and it is frictionless. So if you just give a moment or apply a force on this member, this will freely rotate. So rotation is not resisted. But if you try to pull the member, then you cannot pull because this is fixed. So it can resist forces but not moments. That is a pin. So that is a property of a pin joint. A single member connected to a pin can freely rotate. So that is one thing to note. Okay, so this is additional some information. There are also two terms which are used in structures. One is purlins or rafters. So for a truss system, in a roof truss. For a roof truss, if you use the roof, then basically you will have some sheet which is covering the roof, and basically there are some horizontal members and these inclined vertical members. So these are basically rafters. These members are rafters and these members are purlins. Okay. Here these are purlin. The horizontal members are purlins, and this you can see inclined members are rafter. This is just for the terminology. And there is something called cantilever truss. Cantilever is a very common terminology which is used many places. So cantilever means one end is fixed to some structure and other end it is free. So it is fixed on one side. So you must have had cantilever beam, cantilever veranda, etc. So basically what it means is that one side of the structure is fixed and the other side is free. Like you normally have your veranda or balcony like this. So it is fixed to the main structure, and it is that this is projecting out. It is just free and there is no connection in the other end. So now I will show you a figure, and I am sure you will be able to tell what it is. Can you tell me what it is? What figure it is? What it is basically? Yes. Very good. It is Howrah Bridge. So I have brought it because there are some interesting information about it. Bridge. Yes, it is a bridge, and it is our Great Howrah Bridge, which is a gateway to Calcutta from the other side. So these are deck of the vehicles, and this is composed of bridge truss. Can you tell what is the type of truss? Mostly it is used.
It's a cave.
Huh? Okay, so if you see this configuration, it is type of, yes, correct. So basically it is K type. So some information for you. So this is the Howrah Bridge, and some information, technical information. So you have gone over it, but hardly many of us, most of us are not interested in the technical information. But anyway, I brought it because it is also related to the truss structure. So it is for additional information for you. So Howrah Bridge is a classic example of balanced cantilever bridge. So it is a cantilever bridge. So it is actually not supported at both sides, it is supported only in one side. So that is the marvel. Okay, balanced cantilever bridge. The central span of the bridge is 457 meter long, which is shown in the figure, with a suspended span of 171 meter and the cantilever arm of 142 meter. The length of the anchor span is 99 meter. The formation of the cantilever arm and the anchorage arm is a K type that we have seen, and that for the suspended span is an N type. Adoption of a K type truss helped in the reduction of the slenderness effect of the large vertical load. So this is how the construction of our Howrah Bridge is there. So it is a glory, I should say. So basically it is a marvel also of engineering design. So it is composed of K type and N type. These are a few details which just for your additional knowledge, that's all. So this is the configuration of the supports on the bridge. These are roller type supports. That means it will have only forces on the component structural member vertically up, and here is a rotation where you have Rx and Ry, and this here pin you will have only that vertical. This Ry will be transmitted to this load. Not here. Here this N, you have this N, and this only N, the normal reaction will be transmitted to this member. Okay, now we'll discuss a bit on this stability, and we'll first talk of stability. So you see a figure in which the heavy car has moved across the bridge, and there is no failure in this bridge, the truss. It is very stable. But for this case, there is a man on a bicycle rider, but when he has entered this zone, this part of the bridge, the second half of the bridge, there is a collapse. Can you tell why, based on what we have discussed so far? Why there is a collapse over here, but this car has moved safely? What we have discussed. So we have discussed about the configuration of the truss. So what is a stable configuration? All should be having triangular, it built up of triangular shape. Here it is basically polygonal shape, and it is very unstable. So when it enters the polygonal shape, when it enters the truss where the support structure is polygonal, there is no triangular configuration available, then there is an entire collapse. But here all the configurations are triangular. It is built up of the triangular configuration. So it's a built up triangular pieces are basically placed side by side to build it. So that is a simple truss. So there is a collapse over here completely, but here it is stable. Okay. So now there are two concepts: the stability of the truss. Stability we have seen, there is collapse in the structure. But there are certain cases. Supposing you take this truss, this is basically triangular truss, and it should be stable, but it is having only rollers. If I give a small push, then entire the structure will move to the right like a rigid body, like a chariot, or you have your rolling baggage. You just for a wheelchair, you just push, it will move. So this case, there is no deformation of the members. That means there is no change in the configuration of the internal member. This remains as it is, but the entire truss moves as a rigid body. So this type of situation where the entire structure moves, and but there is no deformation or collapse of the internal members, it is called externally unstable stress. Okay, this is externally unstable stress because you cannot satisfy the equations of equilibrium for the entire body. Here you have this P, but since there is no resistance, it is having the P, so it will have an acceleration in the horizontal direction. So, but there will be no deformation in the truss because you are all having this triangular configuration. So, this is an external called the condition of external instability. So, this is an example where the truss is externally unstable. So, another example is I have fixed the these joints at A and D. So this truss cannot move. So basically, it is externally stable, but because there is no triangular configuration, so it will collapse. So it will collapse internally, but it will not move as a rigid body. So in this case, the truss is externally stable, but it is internally unstable. Okay. So there are two types of stability. One is the whole truss without deformation can move as a rigid body. And another case, although the truss cannot move, internally it will deform. Okay, so that is the other part. So that is called instability, internal instability, and the external case, the other case where the structure is moving, it is externally stable or externally unstable. If it is moving, then definitely externally unstable, and if it is fixed, so that it is not, it is fixed in place, so it cannot have rigid body movement, then you have to check the internal condition. So whether it is internal stable or not. So basically there are various scenarios. I will just, I will skip them. It is quite common here. So here also you will not have, you have this, it is both externally stable, but again you do not have this triangular configuration, so there will be collapse. So this is there. So now, if we think of structural instability, then basically what is the criteria? How will you know from looking at a truss that the structure is stable or unstable? So for that, for internal stability, we can have an equation, a formula by which you will know whether the structure is stable or unstable. Okay, so this is the classification of the truss based on stability, that is internal stability. For example, if you have your number of members M and joints J and the reactions R, then M plus R equal to 2J is a statically determined structure. Because the forces in the members and the reactions and the supports can be completely determined using symbols, the principle statics alone. So if you have this condition, then the structure is stable. That means you cannot solve for the structure and you can find out the loads, etc. So, but this is not the only criteria. But if the structure is stable, this criteria has to be satisfied. If M plus R is greater than twice into J, J is the number of joints, M is the number of members, and R is the number of reactions. That will you'll understand if you take up an example. If M plus R is greater than 2J, if the members are much more than the numbers which are required for structure to be statically determined, then it is known as indeterminate truss. Then it is known as indeterminate truss. And if M plus R is less than 2J, then you have the mechanism, that is structure can have rigid body motion, it can deform, etc. So this is a condition of instability. So M plus R equal to 2J, this is a condition for stability. It is a necessary condition but not a sufficient one. We'll see just one example that will clarify your concept. So you have this truss system. You have these members and it is joint. So this is crossing, that means there is no joint here. If there is a joint, that has to be a circle. This is overlapping, crossing each other, but not intersecting. So what is the number of members? Number of members is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118, 119, 120, 121, 122, 123, 124, 125 10, and then it should be 11. This is 11. Okay, press this. So there are 11 members. What is the number of joints? You can just count 1, 2, 3, 4, 5, 6, 7. J is 7. So J is 7. M is equal to 11 members. And what is the reaction? Over here we have this Rx and Ry at this is a pin joint, and there is only Rx here. There is only Rx here. There is no Ry because this is a roller. This cannot resist forces in the vertical direction. It is normal, it is an Rx. So we have 1, 2 and 3. So R equal to 3. Okay. This M equal to 11, R equal to 3, J equal to 7. So M plus R with 11 plus 3 is equal to 14, and this is also equal to 7 into 2, which is equal to 14. So this condition is satisfied. But this is not stable because it is not having that triangular configuration. Here the triangle is missing. Okay. So basically this is a case of a situation where the truss is unstable. Although this condition M plus R equal to J, this relation is satisfied. What you have to do, you just bring one redundant member over here and just make a triangular configuration. Here the condition is satisfied, that is the determinacy condition is satisfied, and also it is basically stable. Okay. So this is the condition for this stability for and determinacy for the truss. So M plus R is equal to 2J. That is necessary but not sufficient to classify the structure. So you must understand what is necessary and sufficient condition. That is, you must have studied in your higher secondary mathematics. So it is necessary means if it is satisfied, then this has to be necessarily satisfied. But satisfying only this is not necessary for the structure to be stable. So that is it. If the structure is stable, then it implies that this M plus R equal to 2J is necessarily satisfied, but not the vice versa. Okay, but if it is satisfied, it does not always necessarily mean that the structure will always be stable. Okay, so there is a degree of determinacy that we'll skip now. Okay, so there are some examples. So what is the time basically? So only 3 minutes are left. Okay. So we'll take up a few more examples of determinacy. So you take this example. So basically here for this you have if you count, you have 1, 2, 3, 4, 5, 6. How many members you have? 1, 2, 3, 4, 5. We have 5 members, and 3 are supports Rx, Ry, and R4Y. So 3, and number of equations is number of joints. That means 1, 2, 3, 4, 2. So J is equal to 4. So this 8 minus 8. So it is satisfied. Okay. So this is statically determinate. So here, if you do the same thing over here, same equations over here, so you will get number of equations is 2 into 4. That is the same. That is the joints are here only. 1, 2, 3, 4. Okay. Number of equations 4. Number of unknowns is 3 plus 6, 9. So 1, 2, 3, 4, 5, 6. I think is counting this also. It will be made clear whether this is counted or not. So if there is a joint or not. So here it shows number of unknowns is 6 plus 3, 9. So it is statically indeterminate structure. So M plus R is less than 2J. Okay. M plus R is greater than 2J. So number of unknowns is 9 and your number of equations. So what it means is, I'll just explain to you what it means is, if you want to just understand this genesis, the origin of this, origin, the principle behind this equation is, your number of unknowns is m plus r. And number of equation is 2 into j. So supposing you think in this manner, you have two variables and x and y. In order to solve them, you will have two equations. So one for x and with two simultaneous equations. Then you can solve for these the variables. So it is the same way. The number of variables is m plus r, and the number of equations is basically 2j. So if you have your number of equation equal, then you can solve. If you have your number of equation less, then basically it becomes very arbitrary. You cannot solve. You cannot have a fixed solution. And if you cannot, if you have number of unknowns more than the number of equation, then it becomes indeterminate. You cannot solve at all. Okay. So it is like that. If you have number of unknowns less than the number of equation, then there is no solution basically. Or it can have. You cannot have unique solutions. You can have we can have non-unique solution, but will not have unique solution. And if number of equations, number of unknowns is greater than this number of equation, that is 2j, and so basically it is indeterminate. So you have to cannot solve by assuming this structure as rigid. You have to assume that is some deformation, and from there you have to calculate that. So that is it. So why it is 2j? Why the number of equations in 2j? Because at one joint, how many equations are there? As we have seen, normally for a planar system, 3: fx, fy, and fz. Fx, fy, and mz. But in the joint, basically you are having forces are concurrent. So the moment there is no momentum, so the moment relation is automatically satisfied. So you have to have sigma fx is equal to 0 and sigma fy is equal to 0. So that is for a joint J. So at one joint you have two equations. One joint, two equations, for J joints you will have 2J equations. And if you have same number of variables, unknowns as the same number of equations, then you can solve. So that is the intent. So okay, I will end my lecture here today. So any doubt so far? So otherwise we'll end the class. So we'll move on to the next. In the next class, we'll discuss how to solve the determinate trusses. So there are two methods. One is method of joints and method of section. That we'll discuss the details in the next class. Okay. So we will now end our class today. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.
Welcome. So I'm just signing off now.
Yes, sir. Attendance gone.
Attendance, I think Roshni will take the attendance.
It has been taken.
Doesn't take it.